how can we extend? So we'll touch upon that. Then frequency response. The two main responses out there in literature, it's Wagner function and Tudorson function, 1938. This is German, this is American. And you can imagine, so Tudorson determined the frequency response. The Bode plots for unsteady aerodynamics. So this is K, and by the way, let me just go back here. Actually, Wagner presented this function as in non-dimensional time. It's typically it's denoted by S, and it's Ct times U. So this is now meters divided by half chord. Half chord we're gonna denote it by B. Okay. So B is C over 2. So this here, you reach steady state in how much time? This is around 6 to 8 Bs, which is 3 to 4 chord length. So you have your airplane moving on the tarmac or whatever, and your lift will build up from whatever value, say 0, to your steady value in 3 to 4 chord length. This is very, very short amount of time. So let's compute it for a representative example, maybe 737. The chord is around 3 meters. Maybe in flight, I don't record the cruise speed, but let's use 900 kilometers per hour. This immediately gives you, or maybe on the tarmac, takeoff or landing, maybe around this value. This will give you the time that it takes for your lift to build up around 0.04 second, 0.16 second. So this is indeed negligible for an actual airplane if you consider the time scale of the dynamics of the airplane itself. So this is why we use to, even during maneuvers for a civil airplane, even during the maneuver in our flight dynamics course, we consider the aerodynamics as a game. We just multiply alpha by something, right? So your stability derivatives are just numbers. This is an algebraic relation. It's not a dynamical system. From the airfoil motion or airplane motion to aerodynamic loads are algebraic relations in our typical flight dynamics course. But if you have a rapid maneuver, like the Cobra maneuver that we showed, or if your application is entirely unsteady, like flapping bird or flapping insect, then you cannot neglect this time scale at all. Okay? So it depends on your application. Or if you are in flutter analysis, so your wing moves rapidly, then again you cannot neglect this unsteadiness. So there are times that we can really neglect the unsteadiness. Similar to the way we non-dimensionalize the time, the community used to non-dimensionalize frequency by the same thing, so omega b times u. So k is the reduced frequency, like s is non-dimensional time. So the Bode plot, or the frequency response, this is what Tudorson found. This is unity here, and it goes, for infinite frequency, goes to half. This is C of k, which is, it's the transfer function in the frequency domain. Our transfer function is what? Output divided by input. Tudorson input, you consider the steady lift. So how much unsteady lift will you get out of your expected steady value? If you're operating steadily, you will get some steady lift, which is 2 pi alpha. But now, because I'm doing it fast, I'm losing some lift. You can see here that the ratio is unity, and it's the maximum value if you are at 0 frequency. So at 0 frequency, you're doing it steady. So you recover the steady value, but as You move faster, you increase your frequency, your magnitude of the transfer function, C of k, goes less. So your unsteady lift, at least for the small angle of attack applications, your unsteady lift is always less than your steady counterpart. Okay? Unsteady lift is always less than the steady counterpart in small angle of attack, because in high angle of attack it's a different thing. Steady counterpart. Any question about this story? Any question? Yes, Sonali?
From the graph, the frequency response is 1 times is that a ratio, 1 times for the y-axis.
You mean this?
Yes.
So the y-axis is this C of k, is your transfer function.
So it's 1 times c of k.
No, the C of k is equal to 1.
1, okay.
But the C of k is your transfer function, so it's output by input. So in order to get the output, you're going to multiply your transfer function, which is 1, for example, by the input. So this is the unsteady lift, your output. This is the steady lift, your input. Okay? And you recover this guy by multiplying whatever steady lift is expected times your transfer function. Your transfer function gives you 1 if you're operating steady, for sure. But if you're operating with high frequency, you'll get much less. Okay? Any question about that?
No, no question. Well, what would be like the different case, like when there's a high angle of attack, like what would be the reason for that?
I'm sorry, say it
Like
again?
if there's like a high angle of attack, then what would be the reason of the difference in this?
Because this is a very good question. Navier-Stokes equations are nonlinear in general. So when we're studying here the response at small angle of attack, it's as if we're getting the linearized response. The linearized response of any system is only valid for a small neighborhood. And for a general nonlinear system, the output actually depends on the magnitude of the input. This is an important thing. Let's tackle it here. It's an important concept. So, it's an important concept, sometimes it's confusing. So here we can say what do you call aside or digression. If you have a system linear, this is y, this is t, this is the step response due to one input, okay, value 1, step. The step response due to value 2 input. The step response due to value 3 input. It doesn't matter, it will take the exact same time, the exact same overshoot, okay? Which is interesting if you think about it, because for an airplane, for example, to reach 5 degrees or 3 degrees, 5 degrees, say 5 degrees pitch angle, we're saying that it will take the exact same time as if it reached just 1 degree angle. So it's interesting in that sense. Okay? The exact same dynamical behavior. But for a nonlinear system,